everyone, my name is Shreya Dhara, and this is my Physics 2212 Lab 1 video. So the purpose of this lab is to show how a charge separation and distance between two charge tapes can occur when both of the tapes are charged, and we had to find the magnitude of the charge acting on this upper tape B. So to give some models as a background, this mostly focuses on the electric force and electric field formulas for point charge. So for electric force, we can say that F equals QE, where Q is the charge and E net is the net electric field. And from here, we can say that the net electric field is equal to 1 over 4 pi epsilon E, which is 1 over 4 pi epsilon, which is a constant, times Q, which is our charge, over R squared, which is the magnitude of separation squared, times R hat, which is our unit vector. And then the R vector is the difference between the R observation point and the location of the charge. So from using these formulas, I was able to do some math here on the right and say that, well, we know that the force of gravity is going to be equal to the electric force because the tapes are motionless in this diagram. So from there, I did some calculations where I set the magnitude of the electric force equal to the magnitude of the force of gravity. And from here, we can solve for Q, which is a charge, which is going to be the square root of mgr squared over k. And here k represents this constant of 1 over 4 pi epsilon naught. So to give a preview of my results, I got that the force on the piece of tape is 2.76 times 10 to the negative 6 coulombs. And then here's my initial condition. So the system is going to be tape B. The surroundings are going to be tape A and gravity. And then I listed all the constants and conditions I had here. So the distance between the two tapes, the length of the tape, the mass of the tape, the width of the tape, length of an atom, the UFPES, which is like our K, or 1 over 4 pi epsilon naught, and then the charges of a proton and electron. So for the experiment details, what we did is we measured an 8-inch piece of tape. Then we checked the exact length and width of the tape with a meter stick, and we placed the edge of the tape down and create like a handle so it wouldn't get stuck to the table. Then we created another piece of tape, labeled it U, and placed it on top of the first piece of tape, and then we ripped the upper tape off the lower tape. We did this again to make a second U tape, and then we held one U tape above the other and used a meter stick to measure the distance between the floating tapes. So here's some visuals of what that kind of looks like. This video in the middle shows how we created the U tapes. And then this is like an example of the charge separation between the two tapes on the left. This is not the exact picture that was used in our experiment, but it is one of the ones we used where we were looking at the differences between like the repulsion between the two tapes. And then this diagram on the right kind of shows what it would have looked like for the floating tapes. And then for my glow script, basically going off of this map here on the right, I just kind of converted that into glow script. So I figured out the charge of the tape, which is the square root of mgr squared over k. And then we were able to divide the charge by the charge of one proton, or one electron, sorry, to figure out how many atoms for every electron were lost. And then we were able to do some more calculations to figure out what the electric field was going to be, and the electric force. So some of that is outlined down here. And so for our results, we got that the charge on the piece of tape is, again, 2.76 times 10 to the negative 6 coulombs. There are 1.73 times 10 to the 13th electrons lost on one piece of tape. There are 811 atoms for every electron lost on one piece of tape. And the electric field at tape B due to tape A is this value right here. And the electric force at tape B is 56 newtons in the y direction. So to compare the data versus the model, in this experiment, we used real-world data, such as the measurements of the tape, to input into a computational model. So in the real world, there may be air resistance acting on the tapes, which we kind of ignored in this model here. Also, we treated the tape as a long point charge with all the charges centered in the middle of the tape. In real life, there may be some unevenly distributed charges that we just kind of disregarded in this model. And then other sources of error include that tapes may have touched other objects in transit, and again, there may have been air resistance. So what if the electrons had positive and the protons had negative charge? Since both of the tapes repelled each other, they even if the electrons and protons switched charges, they would still continue to repel each other because they would still have the same charge values. The two tapes would still repel each other. And then why is this important? Well, when tapes interact with other charges, there may be a change in the distribution of charges because they're interacting with these other charged or neutral objects. And that's it. Thank you.